there seems to be nothing really working. Any state can go to any state. Some molecules have that behavior, some molecules have this behavior, and so on. So what Frank did was, he came up and used the dynamics of the whole process as an argument to tell you which state can be connected to which state. And what did he do? He said the following. And that was this. Let's say I start the molecule from B equal to 0. And it has to go up. B equal to 1, B equal to 2, B equal to 3, and so on. So I go from here to here. What's the typical time scale in which an electron makes a jump from one orbital to another? 10 power minus? Minus 15 femtoseconds. It's extremely small. In about a femtosecond, the electron has actually found its new home. You start from one orbital, you're in another orbital, in no time it's up there. So in other words, the time scale for the electron to jump from one orbital to another is actually of the order of femtoseconds. 10 power minus 15 seconds. So in 10 power minus 15 seconds, if you throw light and the molecule decides to absorb that light, and we saw that, the molecule has to decide to absorb it because there are so many conditions for it. Frequencies have to be the same, the selection rules must be valid, and so on and so forth. But if the molecule decides to absorb the light and make an electronic transition, the electron will actually take about 10 power minus 15 seconds to make the jump from one level to another. In other words, if the molecule has absorbed light in no time, it's up in a new potential. So it was very happily vibrating according to this potential. And if it absorbed light, what happens? Boom, it's out here. And within 10 power minus 15 seconds, it has now got into a new potential and it was vibrate along this potential. And the time scale, therefore, this is what I meant by saying that Frank used the dynamics of the process. Extremely short periods, 10 power minus 15, femtoseconds. Electron is out from one orbital into another. It's up there. How much time does it take for a vibration to occur? Mind, electronic spectroscopy has to do with electrons. Vibration spectroscopy has to do with massive nuclei. And what's the approximate difference in sizes between these two? About 2000. And that is for hydrogen. As the nucleus gets heavier and heavier, that disparity is going to be even greater. But roughly, if we are talking about 3 orders of magnitude difference in masses between an electron and the nuclei, which means that this vibration process has to be much slower, and it is usually of the order of picoseconds or maybe a few tenths of picoseconds. So, on a time scale of an electronic jump, the vibration is a slow approach. It just does this. It's already up there. So the electronic transitions will actually happen on time scales which are like 3 orders of magnitude faster than any vibration process you can think of. So what does that tell you? It tells me this. When the molecule is vibrating back and forth, we don't know at what point in this vibration it decides to absorb the light. It could absorb the light when it is at the extreme. It could absorb the light when it is here. Anyway, so as this molecule is happily vibrating back and forth, photons hit it, and the moment it absorbs the light, it has to go to the new potential and start vibrating over there. The vibration time period is picoseconds. Electronic transition time period is femtoseconds. Electronic transition will far outbeat the vibration process. So which means, when the fellow jumps from here to here, how much do you think would be the change in its internuclear distance before the jump and after the jump? Let's say it's vibrating in the ground state potential and suddenly it has absorbed the photon. It's got a new position. What would be its internuclear distance before the jump and after the jump? Almost the same. Because this process of electronic transition is 10 power minus 15 seconds. This is picoseconds. This is far, far slower than this process. And therefore, during the vibration, if the molecule makes an electronic jump, the electronic jump is going to occur on time scales that are unimaginably faster compared with vibration time periods. Meaning that the internuclear distance before absorption, when it was in state X, and the internuclear distance after absorption of light, when it is now in state A, has to be absolutely the same. I mean, it can't be immeasurably different or measurably different. It has to be extremely equal to each other. In other words, this jump from here to here entails that the molecule internuclear distance before and after will be the same. But after it has made a jump, what will it do? It will now vibrate as per the dictates of this potential. But during the time of jump, it cannot change the internuclear distance. If it made the jump when the internuclear distance was 2 angstroms, after the jump, it's 2 angstroms. And then it can keep changing its position based on the potential that is dictating it to vibrate. But before the jump and after the jump, just before and just after, it has to be the same. This is what Frank recognized. Frank said that there can be no change in the internuclear distance during a jump. What does that mean in terms of drawing arrows? This is the potential and this is my R. Therefore, I have to show an electronic jump by a straight line. I cannot show an electronic jump like this. Why? If I show an electronic jump like this, it means that before the jump, this was my RE, and after the jump, this is my RE. But I know that can't happen. The internuclear distance before the jump and soon after the jump, they have to be the same. And if they have to be the same, I have to show the transition by a straight line that's absolutely vertical. And that's the reason why we sometimes call these as vertical transitions. So if ever asked you to show me a jump from V equal to 0 of the ground state to V equal to 1 of the excited state, and you show me a transition that's like horizontal, I mean that's something like tilted, it's wrong. Frank's statement is right away violated. Frank's statement says that the internuclear distance just before the jump and just after the jump have to be the same. And if they have to be the same, it has to be. But this, of course, is rather trivial to understand. If something is so fast, this is what is expected of it. You don't change in internuclear distance before and after the jump. Well after the jump, yes, it will change. Because now it has to vibrate as per the dictates of the top potential. And what applies for absorption also applies for emission. The molecule jumps from here to back here, meaning it's returning to the ground state by emission. Again, the electron is jumping from one orbital to another. And therefore, again, it must be a femtosecond process. And therefore, the internuclear distance before the jump and after the jump in an emission must also be the same. So, if I ask you to show me the emission from V0 to V0, how would you show it? Something like that. So, I have to get to 0. But I can't do this. That's wrong. Because if I do that, I'm actually changing my arm during a transition. And if you do that, Frank is going to be extremely unhappy. Because it has to be a vertical transition that you must talk about. First. Now let's look at something else which Frank said. And to do that, let's try to understand the potential a little carefully. And this is my R, and let's say this is V equal to 0. At this point, what happens to this oscillator? It goes up and then it comes back. Go back to your pendulum experiment. And what does the pendulum experiment do? It goes up, stays there for a while, and then comes back. At this point, what happens to the energy? Is it completely potential or is it completely kinetic or is it a mixture of both? Completely potential. Somewhere in between, it's both. But then the total has to be the same. So what has essentially happened is you have taken part of the potential and converted that to kinetic. Somewhere out here, it's completely kinetic. Again, it's potential plus kinetic potential. So as the pendulum operates back and forth, it's actually converting potential to kinetic, back to potential and back and forth. And in the absence of any damping processes, the energy has to be a constant for the entire process. We know that. The same has to be the case for this oscillator too. At this oscillator, at this point, what's the energy? Potential or kinetic? It has to be potential. It's at the extreme end. It has to be the potential. And what's the potential given by? This much. At this end, what is it? Completely potential. And how much is the potential energy? This much. So here the potential energy is this much, here the potential energy is this much. Somewhere over here, what is it? It's completely kinetic. Why is it completely kinetic? The potential at this point is 0. So this must be completely kinetic. This line over here is actually the line of total energy. So this was potential. At this point, it's completely converted to kinetic. At this point, it's back to potential. What do you think happens over here? This much and this much. There are two things. What is this actually? That's the potential part. And what is this here? Kinetic part. So if I drew a vertical line downstairs, what does it actually, what does it mean really? That part of the line inside the curve has to be the kinetic part, and that part of the line outside has to be my potential part. This is completely outside, therefore it's potential. This is completely inside, therefore completely kinetic. This kinetic and this is potential, and at any given point in time, this sum must be the same because the total energy here is actually the same. So when you look at the potential energy diagram, you can actually partition out how much of the energy is kinetic and how much of the energy is potential. Very easy to do that. And all you have to do is just see what fraction of the line is sitting inside the curve and what fraction of the line is sitting outside the curve. The one that is sitting outside must be the potential energy part. The one that is sitting inside must be the fraction corresponding to the kinetic energy. Now, this is where Frank made another wonderful suggestion. And he said, when this fellow is going back and forth, and suddenly you have made this excitation, femtoseconds, it's up there. We already know the position cannot change. But while it is rotating, vibrating back and forth, what can you associate it with? Kinetic / potential. Right? If it is the extreme ends, it's all potential. In between, it's partitioned out. Other extreme end, it's completely potential. Now let's say this guy makes a jump from here up there. At this point, what's the velocity of this moving part? It has to be 0, because the kinetic energy is 0. So the velocity here is 0. The velocity here is 0. And in between, what would be the velocity? It would be whatever that is realizable based on the kinetic energy. At this point, the velocity is going to be the largest. The velocity here will be less, 0, and back again. So associated with every point on this line with a certain kinetic energy, you can actually figure out what the velocity of this vibrating species would be. Half a t-square. It's pretty straightforward. So at this point, velocity is 0. At this point, velocity is 0. But at every other point, I can actually tell you what the velocity is going to be because I can tell you what the kinetic energy is going to be. And therefore, it's possible for me to figure out what the velocity is of this vibrating species at every point on its travels. Now, I make a transition. Let us say from here. At the point of the transition, what was the velocity of the moving body? 0. But then this, and velocity is associated with nuclear motion. But the electronic jump has taken place in 10 minus 15 seconds. So what should be the velocity soon after the jump? It has to be 0, because it can't abruptly change the velocity. So therefore, there are two things that Frank said will happen. He said, the intermediate distance cannot change. And what else will not change? The velocity cannot change. Or it must have the same kinetic energy just before the transition and just after the transition. And unless you keep these two things in mind, and unless the molecule obeys these two little fundamental tenets, the transition is not possible. Because you can't think of a molecule making a traverse from one state to another in which the intermediate distance is abruptly changed. in which the velocity has abruptly changed. That's not possible. Therefore, you must have a transition only if the internuclear distance is the same, which essentially means I must draw vertical lines and not slanting lines. And point number 2, the transitions must involve conservation of kinetic energy before and after. I can't abruptly change my kinetic energy because I can't abruptly change my velocity in this tempo minus 15 seconds. The nuclear motion is very slow compared with electronic motion. So he used these two ideas, and then he said, now I will tell you which transitions are going to be allowed and explain all the things that we mentioned here. Some transitions go from 0 to 0, 1, 2, 3, some go from 0 to 10, 11, 12, 13, and so on. How? Take this. I start from here. If I go from here and I want to go to 0, can I go to 0 from here to here? Because the only way I can go to 0, I have to draw vertical transitions, right? If I have to draw vertical transitions, I have just my 0. I can't go to 0. The only way I can go to 0 is if I say, well, I can do this. No, because it's slanting. You can't do this. So straight away from here I can't go. Let's say I can go from here. Maybe I can. But what's the problem here? The kinetic energy here was 0 because it is starting with the edge of the potential. But what's the kinetic energy here? It's non-zero. So which essentially tells me the way the two potentials are located, the way I have shown them, 0 can't go to 0.